Please join me in welcoming Dr. James Finley.
Well, thank you for the
Joining
introduction. Can you see me and hear me okay?
Yes, you look great.
Excellent. Yes, I just wanted to thank everyone for joining us this evening to come hear a little bit about the work we've been doing in my lab. So I'm an associate professor in the Division of Biokinesiology and Physical Therapy at USC. And I'm going to talk today a little bit about some of the work that we've been doing over the past several years to really reimagine mobility training and how we might be able to use what we refer to as immersive technologies for mobility training. So to begin, I just want to highlight and just, I guess, remind us all that mobility is really a fundamental component of the human experience. So when we talk about mobility, we can think about that in different ways, right? I can think about how I can move parts of my body relative to other parts, right? I can move my head relative to my shoulders or my hands relative to my body. But today I'm primarily going to focus on a form of mobility that's really about how we transport our bodies through the world. So even as really young children, we really see that being mobile is one of the primary ways that children communicate emotion, right? Whether they're playing with their friends, when they're happy, they see their friends, their natural tendency is to run, they skip, they hop. And we sort of fall into that dynamic as well when we start to play with our children, right? We spin them around, we pick them up, we run with them. And this is just a really fundamental way that we communicate emotion with one another. And of course, mobility is also really important for maybe more mundane things. So you can imagine, the things that we do for our jobs. So, there are a large segment of the population that move and need to walk and be mobile for their jobs. And then, of course, we use our legs to just transport our bodies from one place to another, right? Whether it's walking down the street or walking through an airport. Now, one of the, when we think about mobility, this is something that we often do without really thinking about it much. However, we know that this ability is dramatically impaired when we have damage to what we call the neuromuscular system. And I'm just going to highlight one example. So for those of you who don't know, Parkinson's disease is what we call a degenerative neurological disorder. And we commonly think about Parkinson's disease as being characterized by the people who take slow, short, or small steps. We might think about people who have what's called a resting tremor. And these are often the major hallmarks that we think about if we know of someone who's had Parkinson's disease. What we often are maybe less aware of is the fact that Parkinson's disease also affects parts of the brain that are involved with what we call cognition. And so this can affect or impair the ability for some individuals to plan movements, to shift attention from one task to another, and to order a sequence of activities. And this is really important in the context of mobility because oftentimes when we move in our environment, whether we are crossing the street, moving in in this case, in a shopping center, we often have to make plans about where we're going to move, how we're going to move based on properties of our environment. So this is actually a cognitive motor challenge. And one of the things that is associated with these cognitive impairments is an increased risk of falls in this population. And this is not only true for people with Parkinson's disease, but there are similar patterns that occur with natural aging. So just as we get older, sometimes we have cognitive challenges that impair our mobility. And this also happens with people with other types of neuromotor impairments, such as stroke, which is one population that we also study in my lab. Now, in the lab, we're primarily concerned with understanding how what we might call these different states of neural function. So whether somebody has had a stroke or somebody who hasn't had any neurological impairments. And we want to understand how these different types of neurological states influence mobility. And when I talk about mobility, there are many different things that we can measure. And I'm often concerned with measures of what we call locomotor function, things like energy, cost, and balance. And we want to understand how changing the way that people walk influences these measures of function, because ultimately we want to use that knowledge to both inform the context of physical therapy, right? So what it is that our colleagues in the clinic do with their patients. And we want to do that so that they can improve their lives out, so the patients can improve their lives outside of the clinic. So this is just an image of the lab, just because I think most people have not seen the type of space in which we do our work. And so this is a lab located on the Health Sciences campus at USC. We have a motion capture system, so you'll notice that there are cameras around the top edge of the room. And those cameras, along with markers that we often place on our participants, allow us to measure how people move when they're in the lab. Now, we have all sorts of other, we call them toys, but really they're measurement instruments. So things like sensors that measure muscle activity. We have devices that measure oxygen consumption. And all of these things together allow us to paint a picture of how a person is moving, how their muscles are coordinated during movement, and many other things. And in the lab, we study people while they're walking either on our treadmill, which you can see in the back of the room here. We've strategically placed it or embedded it in the floor so that our participants can just walk directly on and don't have to climb stairs or anything. And then what you see in the foreground here is something I'll spend a lot more time talking about today, and that's a virtual reality system. And so I'll highlight some of the advantages of VR in the coming slides here. So when we think about the objective of physical therapy, and this is just a sort of a schematic of what happens, right? So when an individual or family member or someone in their family member come into a physical therapy clinic, generally they have some sort of impairments with their ability to move. That could be mobility in the whole body sense that I've described, or challenges with other parts of their body. And once in the clinic, they will work with our therapists through several sessions over many weeks to improve their capacity and their ability to do more challenging tasks. And then the objective, of course, is that will allow them to do more of the tasks they find meaningful in the real world. And one of the challenges in this sort of path here is that the real world is very different than what we might see in a typical clinic. And so that discrepancy can often affect how much people, what they learn in the clinic generalizes or translates to the real world. And so a lot of our work is using technology as a way to try to bridge that gap in some sense. So we use a technique that we refer to, or that is generally called virtual reality. And this essentially involves a headset that you place on your head. And the real innovation that makes this so much more possible now than it was even 10 years ago is that the technology inside these headsets is essentially the same as what you have in your cell phone, right? So in some ways, I mean, you're actually carrying around a VR headset in your pockets. You just need a special device to hold it. And this can be used to recreate 3D virtual environments. And so for us, this is really important because this allows us to do what we call multi-context training. And it allows us to provide graded exposure to varying environments. And so this is, our therapist colleagues are extremely creative in how they use their space and the tools available in that space to vary the level of challenge for their patients. And here we're able to now add to that by creating visual scenes, mimicking real world challenges through things like obstacles or crowds, and then doing so in a way that's really systematic, right? So that's really key for us because that allows us to tailor the level of challenge to the needs of the patient. And so if some of you may have never seen one of these systems before or experienced them. I think probably one of the more maybe general ways that people have come to learn about these is through this movie, right? So hopefully many of you have seen the movie Ready Player One. And this is, I think it's set maybe 30 years from now. But one of the fundamental aspects of this movie is that people can enter these virtual environments and experience them as if they are real. And where this movie is set, they have much more advanced technologies than we do. So not only can they create a visual environment that feels or looks real, but they also have the ability to provide what we might call tactile or haptic feedback so that people have a sense of touch in that world. So when you can control the information that's coming into all of the senses, now you actually have a tool where you can literally recreate people's reality. And so this is where a lot of the technology is going in this space. But this is not where we are right now, of course. So when we're again primarily interested in mobility and ways that we can use VR to study and train people to improve their mobility. And so when we first got this device a few years back, there was almost sort of no work that was being done to study how people use or walk in virtual environments. And so along with this is one of my, I guess now former graduate students who recently finished her PhD, but she and some of our other colleagues would develop virtual environments, interface them with our motion capture system, and allow us to study things like obstacle negotiation. Right? So one of the really interesting things that you may not consider about VR is that when you place one of these headsets on, it actually, you no longer have a body, right? And so all you can see is what's in the headset. And so one of the first questions that we wanted to understand was, do people even need this information about their body? How might do they use it when they're walking? And so we often will create experiments where we make custom virtual environments. We manipulate some feature of that environment to ask a scientific question. And so here the scientific question was, to what extent do people use visual information about their legs when they are stepping over virtual obstacles? And so we can provide different types of visual information, right? Control condition where there's nothing. We can provide information just about the feet with the endpoints, or we could provide, sort of what we call a link segment model, where now you have some distance or length information about your own, thigh and lower leg. And I mentioned earlier that we have different tools that we can use to measure people's movement. And so in this case, we measured what's called the head angle. So this is just a measure of how much people were looking up and down. And let's see if I can, there we go. So here we can see that this is a measure of how much people are looking down from horizontal. And as people approach the obstacle, it's not all that surprising, but we can measure how they look down toward the obstacle. When they cross over, they look back up toward and then straight down their path. Now, the question here was, how is this, this is what we call a proxy of their gaze. So how does where they look relate to where they are relative to an obstacle and the information that they have about the legs? So there are several findings from this study, but one of the things that we found that we thought was really important was that when you give people visual information about their legs in VR and you ask them to step over obstacles, they use that visual information. And so we measured this by looking at the relationship between their foot clearance when they stepped over the obstacle and the head angle. And if those two things are related, then that is one way that we can infer that these things, that the person is coordinating these things. And we found a much stronger relationship when people had more information about the body. And so this is a way that we can use VR to understand something that would be, fairly hard to understand in a typical environment because we always see our body. And so when we think about the use of VR for therapeutic purposes, the ultimate goal is that people are going to learn something in the virtual environment, and then they're going to do what's called transfer, generalize what they learn to the real world. And so in a separate study, this is another study in neurotypical young adults, we wanted to understand how much people transfer these skills. And so for this, we created a task based on a previous publication where people had to cross or step over an obstacle with a desired level of foot clearance that was really close to the top of the obstacle. And so we designed this task specifically so it was a precision walking task, and so that we could compare our results to previous studies. So when we looked at the behavior during this task, on the left, we have a measure of foot clearance. So this is how far above the obstacle was their foot when they stepped over. And then on the lower part of this figure, we have the obstacle number. And so learning, as we describe it here, is measured in part by this reduction in foot clearance. Right? So we can see that at the group level, and for each individual, people all learn to reduce their foot clearance with practice. In addition, if we brought them back 24 hours later, we could measure something called retention. And retention is one of the key outcome measures of these types of what we call motor learning tasks. And so when we brought them back 24 hours later, they still retained the low clearance that they had at the end of day one, which is a measure that they actually retained what they learned on day one. Now, when we move to overground on the right-hand side, we also asked participants to step over a real obstacle over ground, so outside of VR. And the prediction would be that if what they learned in VR transfers to overground, we should also see a reduction in foot clearance over ground. And that's indeed what we found. And not only did they do this on the same day, they didn't just show this behavior on the same day, but they also retained this improvement in performance over ground. So this is one of the first studies that we did that really provided evidence to us that we can use VR to actually have people learn skills that generalize to the real world. And so, of course, we're really most interested in thinking about how we can create training experiences for people with neuromotor impairments. And so for that, we recently finished up a multi-year study to do what we call user-centered design of VR applications for mobility training. And so I started off today's talk talking about challenges that people with Parkinson's disease face. And so we decided to create a training application that really was geared toward this population. I'll talk a little bit more about design later on, but one of the exciting things was that this was, so my background, as you heard at the beginning, is in engineering and neuroscience. And we put together a team with people with expertise in motor learning, physical therapy, interactive media, VR, and interactive design. And so we have a really exciting set of individuals that allowed this project to take place. And so what you've seen so far is people walking with headsets on a treadmill. But really what we want to do is to have people walk over ground, right? That's the challenges that most people face occur when they have to walk over ground and they have to deal with turning and navigating obstacles and things. And so fortunately for us, as we started this program or this project, HTC released a headset called the Vive. And that headset came with its own camera system or camera trackers so that people could walk over ground. And so from a design perspective, one of the first things we had to do is understand how do we even create interactions or interactive experiences with the system. So this is just show a couple of videos to show what this looks like, right? So how is it that we do design for 3D virtual environments? So this is something that we would generally refer to as our apple picking task, but basically we said, okay, we need some task, right? So let's have people walk around and pick these green boxes while avoiding these, let's call them obstacles, right? The tall blue boxes. And we're going to give them some points. So started off really basic because we were really just trying to understand what does it even feel like to interact with a 3D virtual environment when you're walking over ground. So this is, again, a new experience for almost everyone. From there, we wanted to think about how do we actually make this a little bit more challenging. So we added some holes, virtual holes in the floor, made the space a little bit darker. And what you'll see is that there's also a moving obstacle in this case. And so we want to understand how natural was it for people to move away from these obstacles. And as you could see there in the video, and I'll rewind it a little bit, is that when he sees the obstacle moving toward him, he naturally steps back. And so you respond to these virtual obstacles as if they are real. Like no one naturally likes to allow for something to visually move into their personal space. So that was exciting. And from there, we had to think even more deeply about design. And we worked really closely with a team of developers through one of our courses, that course was taught by one of our collaborators who I mentioned earlier. And what we came up with was an application that we refer to as Wordplay VR. And to tell you a little bit about this development process, we, throughout, this is a multi-year development process. We would bring in people with Parkinson's disease. We would take our headset to support groups, and we get people's perspective on, standard VR games and some of the prototypes that we created. What is it that you like? What is it that you don't like? What would you like to see? And we also work with therapists, right? So they're the ones who are going to have to use this with their patients. And so if you can look here, so this is the application, and you can see that there is a puzzle that the person has to solve. So we give them a category. This is a New Year's Day related word. It's January. And they have to find the letters that fill in that puzzle. And so you can see that the user can reach out and grab these letters. They have to step over obstacles. Now that they're over ground, we can have them do things like squat down or reach up. And then they need to walk back over to the puzzle, step over another obstacle, and place the letters in the appropriate location. And so there are various features that we can change to make it more or less challenging. But what you can see here is if you look closely to the video on the left, you'll notice that we now have a wireless system. So there are no cables attaching the headset to the computer. So it really allows people to move freely in the physical environment so that they can interact with the virtual environment. Now, I mentioned already about the fact that our physical therapists are the ones that are controlling this interface. And so we created a tablet-based user interface for them. And what this allows them to do is to first, for each game, each round, they can select a topic. So from a range of topics that their patient might be interested in. In this case, it's animals. They can choose words in that category that have different levels of difficulty. That difficulty is based on how frequently they're used in language, how hard they are to spell, and how long they are. And then you can see that there are several other features or boxes on this interface, such as the number of missing letters, how long the letters stay in place before they move, and many other features. And so the important thing here is that this results in an experience that is replayable. So the person doesn't have to do the exact same thing every time they're in the virtual environment. Right. So we did, use several different ways to sort of measure how well people enjoyed and how their level of interest in the system, because that was our primary outcome, right? We wanted to be able to design a system that people, both the end users, both therapists and people with Parkinson's, actually want to use. And so the system rated really highly when it came to usability. So this is how easy it was to learn how to play. We also found that as the therapists used it more and more, they were able to reduce the time to set up the system. And then we had other measures of interest and enjoyment, which all sort of converged on the idea that this is something that people would like to do. And so this is just one of the applications that we've developed. And since then, we moved on to some other applications that really operate at this interface of cognitive and motor training. So this is one of our more recent applications. So this was developed in what we call the COVID age. And here this is not specific to mobility, but it's a way that we are using VR to understand or to develop more interactive cognitive
Click
assessment.
anywhere to begin.
So here you can see that the player here is actually seated, and the task is relatively straightforward. They have to select a letter and then follow that letter with a word, and then move back and forth from letter to word. And so this is a measure of this individual's, lower the volume, of an individual's ability to switch, right? So you have to first remember what's the order in which you need to select the letters, and then you also need to switch from letter to animal and vice versa. Okay. And so this was developed with a team of computer scientists who were all working remotely during last fall, and they recently presented this at a meeting. And so this is just one example of a scene where it's basically training, showing people how to use the system. Oops. And then here you can see that we think about the user interface. So we want the people to be able to choose a tutorial to practice or to actually play the game. And then there are a range of different settings in terms of the level, how easy it is. This will be the easiest level. Everything's right in front of you, and there are only 3 options. We can add a little bit of complexity, right? So there are more things in the scene. And then this is the most difficult level where there are lots of distractors. So again, because of VR, we can, the sort of ease with which we can create dynamic environments in VR, we can vary the level of challenge and really see, at which point do people have difficulty. Now, so that's a little bit about what we've done just in the lab, essentially. But one of the things I wanted to highlight here, since it's a fairly general audience, is what are the challenges? I mentioned earlier that we do this design in a multidisciplinary team. And one of the things that the challenges that we found early on is that we all speak different languages, right? So clinicians might refer to executive function, disability, or some clinical assessment like UPDRS. Those of us who are more like on the science side might talk about, kinematics and IMUs and PCA, because that's where we live. When we work with developers, they have their own language. They talk about, Git and APIs, the front end, back end of a piece of software. Those of us on the scientific or clinical side have no idea what they're just talking about. And then once you move to industry, there's another set of language. And so this is one of the challenges that we, have sort of faced. And I think we sort of succeeded in being able to do development and sort of teaching each other what all these things mean in their various contexts. Another challenge that is generally present when we think about developing VR applications, particularly from an academic perspective, is that all of the stakeholders have different incentives, right? As a clinician, your primary job is to improve your patient's quality of life, right? How can this help my patient? That's often the primary driver for clinicians, and which is totally understandable. As an academic scientist, we're often concerned about, we want to understand fundamental scientific principles, we need to publish, we need to obtain grants. And so this is the world in which we live. As students, they have a separate set of structures, right? Students are in school to learn new skills, to build a portfolio, and to ultimately find a job. And finally, again, we could think about the industry end of thing with maybe startups, where they're interested in attracting investors and selling software and hardware. Right? And so when we're doing the academic development in the context of health, we're operating at this interface with all of these different stakeholders. So one of the things that we've been trying to do over the years is now to sort of provide a framework where we can have people from these different areas come together and really start to maybe smooth out this, what we call translational pipeline. And so we've done this in part by bringing together a range of researchers through USC who have been working on virtual reality applications. And this has led to what we refer to as our USC Smart VR Center. So this refers to or it stands for the Sensorimotor Assessment and Rehabilitation Training in Virtual Reality Center. And so you can see by the list and the affiliations here that people come from all over the university: physical therapy, occupational therapy, medicine, gerontology, business. And these are people who have been working in this VR space, some for over 20 years, some who just maybe for a few years, but we're all sort of doing things in some ways on our own. And so now we're better able to share resources, and we really want to create a setting where students, researchers, educators, people from industry, clinicians, and artists can come together and really develop rigorous and impactful applications. And so just wanted to kind of finish up the next maybe 5 or 10 minutes here to really talk about what we're doing here. So first, we have a website that we've created that really describes a lot of the work that different people have been doing in the center. You can find descriptions of our projects, examples of our recent publications, and a list of events that we have had in the past and will be having in the future. And we created this so that, as basically a hub to bring people together, right? So if, let's say that you are in industry and you have a system that you need to test, but you don't have the maybe academic or clinical expertise, we might be able to connect you with someone through the center, or vice versa, right? Maybe you've developed something and you would like to reach out to potential investors, and this is another a way that we might be able to do that. We also have a active Slack channel where we all communicate and share different opportunities with one another. And it really, again, provides a face for us so that people know what is happening in our individual departments, but really more so USC broadly in the context of VR. We do have a range of connections in terms of education and outreach. These are a few years old now, but we've worked with several student teams through some of our courses. So the Wordplay VR game that you saw was developed in collaboration with students who you see in the top left through a course. We've had other investigators from the Smart VR Center also work with developers that way. We bring in students, high school students for instance, National Biomechanics Day, and we participate in different hackathons and things throughout the LA area. More recently, over the past year, we've had several different virtual events, and I'll just highlight one today. And earlier this semester, beginning of the year, we had what we refer to as our Smart VR Community Showcase. And again, this is in the midst of the pandemic where we couldn't all get together physically. But what we did was to create an event where many of us who are sort of the co-directors of the center could show the community what we're working on, right? So what is it that we're actually doing? Can we show them demos? And this was a really great event to just advertise what's going on and to really learn from each other. Because oftentimes you don't necessarily know what sometimes the people directly next door to you are doing. And so I wanted to highlight some of this work to really just kind of like show you all what's happening beyond my group, right? This isn't just me and my students, this is a whole sort of ecosystem of developers. And so I'll highlight just 4 of these short versions of the video to give you a sense of the types of things that are happening in the center. So the first is from Dr. Skip Rizzo, who is one of the most well-known people in the world of VR for mental health, and has done great work over quite a long time. So just want to share this really quick.
The point being that this is an evidence-based approach in its traditional format, relying exclusively on imagination. But in our case, we've created 14 different worlds that we can put a person in and help them in the process of confronting and reprocessing difficult emotional memories, but in the safety of the clinician's office. And by doing that repeatedly under the guidance of a well-trained and supportive clinician, we see significant gains and reductions in PTSD symptoms.
So he's been doing a lot of work with veterans with PTSD and showing that virtual reality can be a useful way to reduce their symptoms. And he's done work with many other populations, but this is just one example. And then this is work from Dr. Sukli Liu, who's a professor in our Occupational Science and Occupational Therapy division.
To do this, we created a system called Reinvent, and it takes brain and muscle signals that indicate somebody's trying to move and gives them feedback of their own arm moving in virtual reality, even though their real arm doesn't move. What this looks like in practice is something like this. So this is one of our participants who's had a stroke, and he's wearing an EEG cap, so we're reading out brain signals, especially from both sides of the brain, but we're using the signals on the side that was damaged after stroke. He also has a VR headset, and what he sees in here you can see on the screen. And we're also recording muscle signals from him to see if that in the future could also be a viable option. So what happens in this paradigm is that you'll see a ball come up to the table, and the goal is for him to move his virtual hand towards the ball so that it pushes the ball off the table again. As you can see, he has very limited actual arm movement, but the movement that he sees of the virtual arm is driven by his brain.
So this is some really amazing work where people post-stroke who have may not be able to move their more affected limb, where by placing them in VR and recording muscles from their brain, or signals from their brain or muscles, they can see their limbs moving in VR and help to strengthen those pathways for movement. Next, we have work from Dr. Judy Pa, who's in neurology here.
So here I'm going to show a little video of our VR environment. So you will see me sitting on a bike and exercising. So it's a stationary bike, and that's the physical activity component of it. And then in the VR environment, you can see the cognitive training aspect of it. And so here you'll see these red arrows. These red arrows indicate where to go in the path. So this is considered one of the learning trials. And then you'll see a few other components in the VR environment. So here, let me go ahead and play this. So that's me with the HMD on, sitting on a stationary bike that we built, navigating through our aviary, so where we have our animals and our birds rescued, can see the red arrow directing me to go right because I'm learning a new path. And as I go through, I'm also collecting items. For this specific trial, I am collecting food to feed the animals. So once I get to the end of the path, I throw out the food to the animals. And they have these little heart emojis to show me that they're happy that I fed them and I completed the trial.
So Dr. Pa has been doing some really amazing work with people with cognitive impairment and Alzheimer's. And this VR application has a navigation component embedded in it, which is basically, again, working on this cognitive motor interaction. So people are biking through the park, so there's an intensity to the exercise, and they're combining that with a memory task to basically memorize that map. One of the really cool things about this work is that they've actually recreated, I believe it's Golden Gate Park from San Francisco. So these are, you can take people through VR to places that they would like to maybe go physically. And then last, we have some really cool work from Dr. Tyler R., which is not a motor task. It's not cognitive, but I think it's just a really great way to show what this type of technology is capable of.
The point being that this is an
our project is trying to see how we can augment normal papers, scientific communication, the backbone of how we communicate, with digital techniques, and how we can better represent our data. As as we move forward, nearly everything is digital except for the communication, and this is really designed to bridge that gap and do a lot better. So the idea is you can just aim your smartphone at a scientific paper and see the attached augmentations to those figures. We can do this with 3D models, like that last example. We could do it with videos, like this example. This is another hippocampus data set. These are neurons inside the hippocampus. And the video example, I think, is particularly interesting because so many fields have tons of data types that they can represent very well in video format that don't fit nearly as well in 2D static figures. So this
Yeah, so this is, so altogether, hopefully this gives you a sense of the type of work that, just a subset of some of the faculty and investigators are doing at USC, both in the context of mobility training, which is my work, but also things related to PTSD, improving neuromotor function post-stroke, improving memory, cognitive function in Alzheimer's, and even really creating new ways for us to interact with scientific articles. So with that, I will wrap up and leave plenty of time for any Q&A. So first, I want to just acknowledge the collaborative team that has gone into this. First group of people you see here are faculty at USC, who I've been collaborating with over the past maybe 7 or 8 years now. So some of them are members of the Smart VR Center, some are not, and they come, again, from all over the university. And the second list here are graduate students who currently or have in the past worked in the lab. A lot of the work that you see anytime a faculty member presents their research is a lot of that legwork, and a lot of the hard work is really done by master's and PhD students. So I always want to acknowledge their contribution. And then finally, on the right, we have a long list of developers who worked at various stages of the projects that I showed today. From our early prototypes for trying to understand how to get people to move around in VR, up through the more recent sort of cognitive assessment that I was showing you earlier. And then actually last, but of course not least, are our funding sources. So with that, I'll thank you for your time. And yeah, hopefully you all learned something and found it to be enjoyable. Thank you.